let's review some facts from introductory linear algebra. So a linear system is usually given to us in matrix form as AX is equal to B, where B is a given vector in Rn, and A is an n by n matrix. So given the A and the B, you're supposed to find the X, which also has to be an n vector. And mathematically, we solve this problem, if the matrix is non-singular, by multiplying both sides on the left by A inverse. So this is multiplication on the left. Then we reassociate on the left-hand side of the equation. Then we use the property of the inverse matrix, and then we use the property of the identity to simplify, and so we see that X is equal to A inverse times B. Now throughout elementary linear algebra course, usually there's this long theorem that's built up that has a bunch of equivalent statements, so you might have seen these before, maybe some others as well. So we know that a square matrix A is non-singular. That's equivalent to saying that the linear system AX equals B has one unique solution X for every different B. And that includes the case when B is 0, then X equals 0 is the only solution. So I'll add that one on to this list. It is equivalent to the others as well. We also have that the determinant of A is non-zero if and only if A is a non-singular matrix. We have that the columns of A are linearly independent if A is non-singular. We could say that the rank of A is equal to n, that's the dimension of the column space. And we have that the null space of A is simply the zero vector. That's just exactly the same as this statement in red, only using different words in the definition of a null space. So, mathematically speaking, the problem is solved. Once you find the inverse of the matrix, then you can solve the problem. But that doesn't actually help us too much computationally, because finding the inverse matrix is also not something which is so obvious. So, in fact, when you look at it, there are systems that we can solve, individual linear systems that we can solve without ever finding the inverse of the matrix. So here's an example of a 4x4 system, 4 equations with 4 unknowns. And you see that the system has a triangular structure. So we would call this a lower triangular matrix. Outside of that triangular shape, or above the main diagonal, everything is 0. Okay? Lower triangular matrices have a special structure, so if we look at the first row, the first equation, remember each row is a different equation. We have 4 times x1 plus 0x2 plus 0x3 plus 0x4 is equal to 8. In other words, there's only one variable that appears in that first equation, so we can solve it to say that x1 must equal 8 over 4, which is 2. Now in the second row, we get 3x1 minus 1x2 plus 0 equals 5. But now that we know x1, we can substitute it in. So x1 we said was equal to 2. And so this is equal to negative 1 on the right-hand side. And so from negative x2 equals negative 1, we have that x2 is equal to 1. Okay, third row. I'm going to rearrange this system from the start. So I'm just going to put the 3 times x3 down here on the left side. I also have a minus 1 times x1, but I'm going to move that to the other side. And I have 0x2 as well, which I moved to the right-hand side of that equation. Well, I already know x1 and x2, so x1 is equal to 2, so this whole side is equal to 2 here. So that tells us that x3 is equal to 2/3. And then finally, the last row, again, I'm going to just write down the single unknown that's left, x4, on the left-hand side, and then put everything else on the right. So I have minus 1 times x1, plus 1 times x2, plus 1 times x3. All carried over from the left-hand side to the right. So I have 1 minus 2 is negative 1, plus 1 is 0, plus 2/3 is 2/3. And so that tells us that x4 must be equal to 1/3. And so there we have a complete solution for the 4 unknowns. So we could write x as the vector, remind myself, 2, 1, 2/3, 1/3. And that is in fact the unique solution, which you can easily check. So that's the solution of a lower triangular system. Here's another system, 4x4, which is upper triangular. Okay, upper triangular can be solved pretty much the same way. The only difference is that we have to start from the bottom and work our way up. So I should have said that in the lower triangular case, we call this method of solution forward substitution. For an upper triangular system, we use what's called backward substitution. Now this upper triangular system has been written in a style that now instead of numbers we just use generic matrix elements, and that pushes us towards something which is more of an algorithm. So if we started at the last row and worked our way up, well, the last equation involves only x4, so the last row of this system can be solved for x4 by just taking b4 divided by u44. Okay. Third row of the system has an equation with just x3 and x4, but now x4 is known, so we rearrange. So this equation should have been, or starts out as, u33x3 plus u34x4 equals b3, which then rearranges into what you see here, solved for x3. Second row of the system, right, if we write that out, it becomes u22x2 plus u23x3 plus u24x4 equals b2. Rearrange that to solve for x2, because at this point x3 and x4 have both been found, and then we can solve for x2 and so on. So now this is written very much in the style of something that we could program, but we would have to use n instead of 4 and I and j to get all of the indices right. There's a code like that in the book for forward substitution already. So triangular systems we can solve without finding an explicit inverse. Also, just as a side note about MATLAB, MATLAB is smart enough to figure out when you have a triangular system and apply the correct kind of substitution automatically. So here you see the same system, the same lower triangular system as above. So I called the matrix L instead of A because it's lower triangular, but they're the same as in the example above. So remember, mathematically, or to solve a linear system, we say L\B. That's the synonym for L inverse B. So this is MATLAB for L inverse times B, mathematically. But what really happens now is that MATLAB detects that it's a triangular matrix, which is really easy, and applies forward substitution without any further prompting, and gets the same answer that we have above. That's true of upper triangular systems as well. MATLAB detects them and applies the appropriate type of substitution to solve them.